Welcome back, quantitative analysis students. Mr. Marchetti, your favorite math teacher, broadcasting to you live out of Egg Harbor City, New Jersey. Today we are going to study rates of change and derivatives, and we're going to also discuss derivative formulas. Today is Wednesday, July 14th. All right, so first let's talk about this idea of rate of change. What is an average rate of change? I want you to think about the slope. Remember what the slope is. I have a straight line. I give you 2 points. You do a little formula, and it gives you a measurement about how slanted the line is. That's the summary of what a slope is. Average rate of change is the next best thing because it's a curve and not a straight line. That's basically what average rate of change is. If I took 2 points on a curve instead of a line, what would happen is it would be different based on where I put the points because it's a curve, not a straight line. So in other words, the slope wouldn't always be the same for every 2 points. That's why for an average rate of change, you have to identify which 2 points you're talking about to find out what the slope of the line would be. Take a look at this picture. It actually does make sense. The black line, which is a curve, that's a function that is not a line, that is not linear. If I think about from point A to point B, the shortest distance is that hot pink line. That line represents what's called the secant. You might remember that word from geometry. It means it cuts through a circle in 2 places or a curve in 2 places. That secant line is a line segment of the big line that has the slope. That slope is the same exact as what the average rate of change is because you have to specify with the average rate of change from what x value to the other x value. Now, remember how slope works. For a slope, you're going to need to have both an x1 and a y1 and an x2 and a y2. For average rate of change, they only give you the x's. They can give you x1 and x2. So you have to use the function and go figure out what y1 is and what y2 is so that you have 2 points, and then you can find the slope that way. That's basically, my friends, the gist and summary of what average rate of change is. It's really a very basic idea. It's just slope again, but you can't do it to a curve because it's not constant everywhere the way it is when it's on a line. All right, let's do an example of average rate of change. I'll show you how basic it is. It's really very easy. You're going to be surprised. If you look at the formula, doesn't it kind of look like slope? Here, the question says, suppose a company's total cost in dollars to produce X units of its product is given by this function. Find the average rate of change of total cost for the second 100 units produced, which is a nasty way to say from X equals 100 to X equals 200. Now, don't worry. You're not going to see a lot of weird wording like that you have to interpret to be X equal. That's kind of a little underhanded when you start reading a textbook, you know what I'm saying? But the point anyway is you're going to do an average rate of change with this function with this x1 value and with this x2 value. Can you figure out what you should do? Can you see what you got to do? You got to come up with 2 points and find the slope of those points. You have enough information to be able to finish creating both points. You have the x1 value for the first point. You could use it to get the x2 value, the y1 value. You have the x2, and you can also use that to get the y2, and then you could go and finish with the cost, with the slope formula. It look a little bit like this. We're telling you that x1 is 100 and x2 is 200. We're also telling you that c of x has this very strange formula. All right. Now, what I want to do here is I want to figure out the slope which has the formula y2 minus y1 over x2 minus x1. Remember that? Well, I have x1 right here. Can I get y1? I should put that down there. I have x2. Can I get y2? Well, if I take 100 and put it right here and find c of 100, and here if I find c of 200, then I'll have my answers. This is a little bit ugly to do with a calculator. I'm going to use Desmos to get this because it'll be quick and painless if I use Desmos. Let's go into Desmos and put it in that way. Again, I'm going to put this function into Desmos. All right. I'm going to go to Desmos, and I'm going to put in y equals 4.01x squared plus 25x plus 1500. And I'm going to tell Desmos, please make this into a table so I can get values. So now I remember how I did that. I clicked edit list, and then I went and then a little menu came up and I was able to select table. And now I have table. I want to find out what happens at 100 and 200. That was really quick and easy, wasn't it? Look, there it is, 4,100 and 6,900. So for the value of 100, we got 4,100, right? And then for the value of 200, we got the value 6,900. So again, I have x1 and x2, and then I have y1 and y2. It's 4,100 and 6,900. So what's the slope? y2, which is right here, 6,900, minus y1, which is right here, 4,100, all over x2, which is 200, minus x1, which is 100. A little arithmetic here. Looks like that's going to be 2,800 divided by 100. Everybody cross your fingers. I hope it's 28. Let's check. All right. So as you can see, it really is a pretty basic idea. It's just that, you know, it's a story. And the story is when you did the slope, it didn't matter what 2 points you picked because a line is a constant thing. A curve or a function that's not linear is not constant. So the points, you can't pick any 2 points. It's different based on what 2 points you pick. So if we're going to tell you we want an average rate of change from one place to another, it's going to depend on which places I choose to ask. And that's why we have what we call average rate of change. It's the answer to what would the solution be if this was linear and I go find the slope. All right, let's take a look at example number 2. I'll read out loud. Please try to follow it with me. All right. Elderly in the workforce. Figure 9.18 shows the percents of elderly men and elderly women in the workforce in selected years from 1970 and projected to 2040. Find and interpret the average rate of change of the percent of A, elderly men in the workforce, and then B, elderly women in the workforce from 1970 to 2040. So for a question like this, first of all, we are looking at a very interesting graph that has like more than one different dimension to it. I mean, you have the X and you have the Y, but more so than that, you have almost a Z or a second dimension because you have 2 different graphs at once. Are you talking about the men or are you talking about the women in the graph? So what we'll do is we'll first zone in on the specifics that they're asking for. I'm thinking about right now how they want you to do it from 1970 to 2040. That means I'm going to focus primarily on these figures and these figures. Because what they're asking you for is an average rate of change. Look, once again, find and interpret the average rate of change of the percent of elderly men and then of elderly women, going from 70 to 40, as you can see here. Now, for the men, which we're using, of course, the blue, the stereotypical blue color, we have 26.8% up front, and then in the year 1970, and then in the year 2040, we have 17.3. It's once again going to be just the slope situation where I put everything together with algebra. Let's go there and put the figures down now. It would look like this. For the men, I have 1970 and 26.8 at the beginning point, and then at the end point, I have 2040 and 17.3. Now I can use these figures to figure out the slope. If I consider it like an old Algebra 1 question from the 9th grade. The slope, remember, is y2 minus y1 over x2 minus x1. And let's label these points. This is x1 and y1. This is x2 and y2. If you forgot about which one goes where, just remember every point is x and then y. So these both can't be x's. They can't be. I've seen students make the mistake of x1, x2 here. That's not right. It's x and then y every single point. So the ones are there because this is the first point. This is the second point. Now, let's put everything into the positions they belong. Y2 is this figure, 17.3. Y1 is this figure, 26.8. And then X2 is 2040. And X1 is 1970. All right. We subtract. Let's see. 17.3 minus 26.8 equals that figure, right? Negative 9.5. And 2040 minus 1970 is going to be 70. So if I divide now by 70, I have negative 0.1314. Now I'm looking at it, I'm thinking, uh-oh, I hope that that's not wrong. It's a little crazy, but it's percentages. Let's see how it comes out. There you go. It's kind of ugly, right? And you know, this is something else that we need to talk about for a minute. Very often when you're doing these questions, you're hoping to get something cute like 15% or 9% and something really awkward like negative 0.14% like that, you know. Get ready for that here in quantitative analysis. You're going to come up with very strange answers. They're going to feel like, it can't be right. That I must have made a mistake, but you know, you have to look very closely and believe that you did it right. Surprise, we did it right. So I'm going to leave the other one to you. I think you could figure out doing the one for the women. It's using the pink figures, which once again would be these things here. Let me highlight them for us. All right. You know, you could use 9.7 this time because you're using the pink one. So you're ignoring the blue figure and going through the same motions with those figures, and you'll get the correct answer of 0.0057. I encourage you to try to do it. It'll make you feel like you really have a good grasp on an average rate of change if you can handle it. And as you can see, this one incorporated interpreting a table. And the other thing you could say now is if you're asked to interpret what does it mean, you could say, well, there was a very slight there was a decline for the men, but there was a very slight increase for the women, and very slight in comparison. You could see how even though they're very small quantities, 0.136 and 0.0057 are still comparable. 0.0057 is significantly very much smaller in retrospect than 0.136 that way. So you could say things like that, and it would make sense looking at this table. That's something you need to be able to do for quantitative analysis. All right. So let's talk about this thing. It's called the derivative. All right. Now, as you can see, when we were studying the average rate of change, we were talking about how we were trying to do the next best thing. In other words, it's not a straight line, so I can't find a slope. You know, but I can give you the next best thing, which would be the slope if it was straight from this point to that point. You know, that's the idea of the average rate of change. Something similar is happening when you're talking about the derivative. The derivative has something to do with if I was to have a curve and then try to examine the behavior of a tangent line at a specific given point of the curve, it can tell you a little bit about what kind of a curve it is or what it looks like when it's in the graph. Let me show you what I mean a little bit, and then we'll talk about these definitions. If you're thinking about a function, functions are like roller coasters, you know? But if you wanted to figure out something about this place right here on this particular place only, or if you wanted to talk about just at this very moment, or what's happening right here at this very specific moment, if you draw the tangent line, which means if you draw the line that only touches that function only in that one little point. Now I'm drawing it with a human hand. Of course, it looks like I'm touching it more than that, but you have to use your imagination to think about how it really is only touching it at that one point only. You know, this line right here tells you a real lot about what's happening at that function right at that very moment when it's moving in that way, you know. And if you think about yourself on a roller coaster going through this, there is a different feeling when you're here than when you're here, and when you're here, and when you're maybe here too. Look at what happens when you're here, and look how sharp the line is. That is a tangent there, and the slope describes that a lot. And I think you might be able to see how connected that can be. You know, that's what we're talking about when it comes to the derivative, because if this is a function here, then the derivative is the slope of any line at that particular point that we're talking about. But remember, like with the average rate of change, it has to be in the context of at a specific point to make sense, you know. And ultimately, the derivative is the formula for what the slope would be at any of those points, based on what point you've chosen and the algebraic expression that is the function. Okay, I know it's really pretty deep, but you know, you wanted to take calculus. What can I tell you? So let's carry on and look at these four different versions of the derivative. The velocity, which is a topic that you might recall from physics or from physical science. Velocity is basically synonymous with speed and direction. And if you think of velocity and how you can think about how that's a rate, that represents something of a derivative. Then we have the basic idea of what a derivative is, algebraically or calculus-wise. And there you'll see also there's a limit, and there's an interesting function notation there. I have another one, marginal revenue. Marginal revenue is the idea of what kind of revenue would you make if you were able to sell just one more product. Marginal means what if you could do one more? That's what marginal means. I'm sure that as business majors, you've heard that expression many times. Marginal revenue, like marginal profit, marginal cost, and marginal anything, is another great example of a derivative. And last but not least, in geometry, with my little roller coaster story I just shared with you, we have what's called the slope of the tangent. And I believe the slope to the slope of the tangent line is a little bit more of a practical way to have a good grasp on what a derivative is. It's basically that as you change rapidly, there is a point. You could take one of those points and examine just that one point. For example, if you were driving at 100 miles an hour and you braked and slowed all the way down to 40 miles per hour and then sped up all the way really quick back up to 100 miles an hour, during those times you'd have really steep changes in the way that your speed is changing. If you did a graph of that, you'd have a very extreme slope. Whereas if you looked at the slope of where you were staying steady at 95 or 100 or 105 or 100, your tangent line would be kind of flat, you know. But when you were slowing down because you were trying to stop, it would totally be a very downward looking line. And that's the idea of what a derivative is, guys. Is it's basically looking at a function and thinking about the points that are at the function and how you can use the derivative to describe what's actually happening at that function. Are you falling down the roller coaster? Are you at the top of the roller coaster going flat? Is this an easy, steady incline? Things like that. So once more to reiterate, there are four different great ways to talk about it. You could think of it as the velocity. You could think of it as the derivative, which is also known as the instantaneous rate of change, as you can see there. And then we have the marginal revenue, and we have the slope of the tangent. Before I move on to the next slide, I just want to mention, please take a close look at each of these formulas, all right? You'll never have to memorize anything in my class, so don't worry about that. But what I want you to do is just take a look at these formulas and try to notice how almost exactly the same they are. Look at them. They're the same formula. They're the same formula. All of them are. And these different little images that you're looking at are nothing more than copy and crop parts of your textbook. And it's all over your textbook, different ways to do derivative. But the bottom line is when you're studying velocity, guess what you have to do? Take the derivative. When you're doing marginal revenue, what do you have to do? Take the derivative. When it's about a function on a graph with x and y, and what is the slope of the tangent line, take the derivative. So in other words, the point is these are all the applications of it. And if you read the book, it's a little hard to interpret that. But as you go through each example, it's another great case of how the derivative is used to model velocity, or how to model derivative, how to model a rate of change, or the slope or the marginal revenue. All right. so we have a couple of examples here. And for all of these examples, even though we have interesting different letters and stuff, like here we're calling it V, and here we're calling it R prime, the bottom line is it's always going to be this, and here we have capital R. If you look, I'll just kind of point to some funny things. Here it's a capital R there, whereas here it's a lowercase f. So what? This is R prime, and this is V. So what? It's all the same old stuff. It's going to be basically this idea more than anything else. It's really this idea here. And then you take the limit at the end. Now, you guys studied limits and you did practice with limits, so you already know how limits work. Basically, the way a limit works is if you have 0, it's approaching 0, you just take the 0 and put it in every position of the variable, like as if it was a function. If you have a problem, you try to factor and play around with it until something crosses out and you barely can like squeeze by, and then you can get your solution. That's what we mean by a derivative, is using this function. Now, there are much easier ways to do derivatives, and we're going to talk about that too in this class, but first they show you like kind of the challenging way. Okay, I see there's a question here. Let's just say. Someone's saying, do we offer extra help for a Zoom session? If you need some extra help, the tutoring center is available. At the end of class, I usually end early and I'm still here until 6:45. So if you want, I could study with you at those times, but otherwise I kind of don't make appointments outside of teaching the class, but I do leave time at the end of class to help students out. Let's see another question. You're more than welcome, and I'm sorry, I just saw that. I didn't know how long that question was sitting there, but yeah, after class, I'm going to be sticking around if you want to ask some questions. I'm here to answer your questions, of course. All right, so what we're going to do is we're going to read this question. Remember, you don't have to be a physics expert. Hint, it's velocity, so you're going to take the derivative. Okay, suppose a ball is thrown straight upward so that its height, f of x in feet, is given by this equation, where x is the time in seconds. Part A says, find the average velocity from x equals 1 to x equals 1 plus h. Part B, find the instantaneous velocity at x equals 1. So what they're trying to do is have you find the average velocity going from the one to the other, which is basically just the numerator, and then divide. And then they want you to find the instantaneous velocity at x equals 1. So how do we figure that out? Well, here's what we're going to do. We're going to take that formula and we're going to use f of x, and we're going to see if we can make heads or tails of that formula, kind of like this. Now, what you're going to see me writing is what you write if you're taking a class with a notebook and pencil. This class is really you're using online a lot more than that. So you're going to be kind of showing that you understand this material through WebAssign by clicking different things, instead of having to write it and submit a written document. What I'm going to write is I'm going to show you basically the process, and just pay close attention to it. Maybe you can watch the video later on and rewind and watch it a couple times to be able to see how the process is with doing the limit. Okay, so first we have a function. The function is 96 plus 64x minus 16x squared. And we're asking you to find the velocity, which is going to be the limit as h approaches 0. And then I'll put the formula in, and then we'll figure it out. Now, if I'm going to ask you to try not to write all of this down right now, just pay close attention. If you start writing everything down in a notebook that you see here, you're not going to be able to follow what I'm saying. You're going to get lost and confused. Then you're going to get to the point where you're just writing it down and you're going to waste your time. Just think about what I'm saying. Try to follow what I'm saying, okay? You can watch the video later. You can write it later if you want. You'll have a transcript of it because you'll have the video. I just want to try to show you how you would get through figuring out the velocity if you have a function looking like this using this formula. First of all, we know what f of x is. It is this formula. But what is f of x plus h? Try to remember that if you have f of x and you have stuff in x, basically whatever you have there, I'm going to use a cloud, for example, you just put that cloud everywhere instead of the x. So if I'm trying to find f of x plus h, let's investigate that for just a minute. instead of f of x being all of this with an x here and then x squared here, I'm going to take this expression and put it in all those positions, those two positions. It'll look like this, 96 plus 64, now times x plus h, minus 16 times x plus h, quantity squared. All over. Well, before we do all over, let me just put a line there. Before we do all over, we're just trying to figure out at this point, what is the quantity f of x plus h? Notice there's also f of x right here as well. So after you write this out and figure out what this is, which is a big headache, and get it all written in there, the next thing you do is you put minus, and then you put the entire function once again. And then what happens is when you multiply everything out, if you're careful with your algebra and you multiply everything out right, things cancel out perfectly, and you'll wind up having something without h in the bottom, because the whole problem with this whole scenario is if you let h be 0, you get divided by 0 right off the bat. And that's the way all of the formulas are set up with the limit, is that the 0 is here and the bottom is h. So what you have to do is work through the whole thing to try to figure out what it would be, and then slash out h somehow. Let's carry on. We're going to do this. First it's 96, and then this is plus 64x, and then this is plus 64h, and then this is minus 16 times a very strange quantity. It's going to be this. Now this, if you remember, you're supposed to write this twice and do FOIL to it. I'll put that kind of in here. X plus h squared, that's the same as x plus h times x plus h. So if you multiply it, let's do that on the side. I'm not going to squeeze it. If you multiply it, what do you get? Let's see. X times x is x squared. X times h is xh. H times x is xh again. And h times h is h squared, which gives you x squared plus 2xh plus h squared. So from now on, whenever you see x plus h squared, remember this little story of how you write it twice and do FOIL, and you land on this. This is a 2 because this is 1 and 1 here. Some students have told me they get very confused when there's no coefficients. Don't let that bother you. Put 1s there if there's no coefficients. Okay? So this quantity right here is what actually belongs in my brackets. And then, of course, if I distribute this through, now I have 96 plus 64x plus 64h minus 16x squared minus 32xh minus 16h squared. That's a real lot of stuff. Also, I'd like to focus on this for just a minute. Now, where is it? Here it is. Minus f of x there. Look at that. See that minus f of x? Let's figure out what that is. If I had minus f of x, it would be minus all of this, wouldn't it? Be minus that whole thing. So I'm going to put in there minus 96 minus 64x plus 16x squared. So in other words, and I'll highlight with color to try to make it clear for you guys, because I know this is really weird stuff, calculus here. But let's see, I could highlight with this. Do the brown. So this f of x plus h stuff is all this stuff, right? This minus f of x is all this red stuff. Now, does anything cancel out? Well, isn't it a miracle that these knock out, and these knock out, and these knock out? And what you're left with is, don't I have a green marker? Yeah, there it is, okay. What you're left with is this one, and this one, oops, and this one. And don't forget that it's all over h. So if I write this on top and over h, let's see what happens. Look at it now. Now it's not that hard anymore. Now I think we can see maybe there's a way to get out, you know? The way you're really supposed to do it is by factoring. If you factor it and write it this way, meaning take h out of each term, it looks like this. Right? So if I slash out the h and the h, this is what I got left. 64 minus 32x minus 16h. Now, if we take this and take the limit of it, because don't forget, it was a limit. You know? Here it is. Remember that it was a limit? I'm going to let this creep in. Here's the formula we're using, the limit as h approaches 0, right? Let's put that limit in there. Let's let the limit approach 0. What does that mean? That means this becomes a 0. So this goes away, and I get this as my answer. So what is the velocity? It's 64 minus 32x. Now take a look at the answers. First, the average velocity is the numerator from before. If we take the quantity 1 and put 1 in, let's go back and find, we put x equals 1 in. So now, what happens when x equals 1? The answer. If x equals 1, this becomes 64 minus 32 times 1, and that would be 64 minus 32, and that would be 32. The solution would be 32 for that one. Okay. Now, okay, now it's really important that you guys just hear me out on this. That was a very long process. As you could see, it involved a lot of very advanced algebra. We had a quantity that was a binomial square that had to be written twice and FOILed out. We had a case of factoring where you use GCF factoring to pull h out of everything so everything crosses out nicely. We also had a limit in there as h approaches 0. And we had all kinds of bonus distributive property, combined like terms. There's a lot of old algebra stuff in there. Now, the good news is you don't have an exam to take where you're going to take a pencil and do that like I showed you. But in a more advanced calculus course, that's what they make you do. When you do your WebAssign practice, you'll see models like that of cases with the limit where they substitute and they work on trying to remove h, the way that I showed you how h slashes out. I'm going to advise you when you're doing your WebAssign homework to make sure you come back to this video, come back to our PowerPoints, come back to my construction paper writing, and try to follow the methods that I went through and use them to answer the questions in WebAssign. All you need to be able to do is demonstrate that you know how it works. You don't have to do it from beginning to end the way I showed. I wanted to show it to you to make it clear to you what the process is, because in quantitative analysis 2, your practice is really just talking about specific parts of how that process works. Okay, so now you can see the way it works. First you find f of x plus h, which is a big task of its own. Then you figure out what the numerator is, which is another task of its own. Then you figure out what happens when you divide by h. You use a little factoring. Then you take the limit, and then you plug in the actual number, x equals 1, into the final solution that you get. And you'll get your instantaneous velocity that way. But as you can see, once again, it's an application of the derivative, which is this limit formula with f of x and f of x plus h in it. Let's look at example 4. Right? Suppose that an oil company's revenue in thousands of dollars is given by the equation, and we have an equation there, where x is the number of thousands of barrels of oil sold each day. Find the function that gives the marginal revenue of any value for x. Find the marginal revenue when 20,000 barrels were sold, in other words, when x equals 20. Once again, you'd have to go through the entire process. I'm going to show it to you one more time. We're going to go through it with 100x minus x squared, and we're going to figure out f of x plus h. In this case, they're using the letter R, but I'm going to stick with the F because it doesn't make a difference which one you do. It's all the same thing. You might as well keep using the F. And when you're through, we're going to go ahead and put 20 in and see what the answer is for part B. For reference sake, here are the answers. Let's have them available now. We will be expecting to get 100 minus 2x when we're through. And we're also going to be expecting to get as our solution 60 grand. Okay, so I'm going to go ahead and write some of that stuff down, and then we'll work through the math together. All right? In all fairness, this one is a lot easier than the last one. This would have been a better example to begin with, to work through, and then then maybe do the other one that we just did second. But anyway, first of all, let's not forget we need to find f of x, and we need to find f of x plus h is our first task at hand. So right now, I'm going to think about everywhere that I see x, I put it here and here, right? So this time I don't see x, I see x plus h. So I'm going to put x plus h there. And I'm going to put x plus h there as well. Okay, let's pause there for a minute. Is that clear how I did that, my friends? Because this is a deep idea. But f of whatever is 100 whatever minus whatever squared. So f of this is 100 this minus this squared. So whatever it is, you have to put it in that position. Drawing parentheses makes it a little bit easier. It makes it like you can write it clearly and easily. Some students kind of lag on that. They say, oh, times, how do I write times for binomial? Parentheses. You will draw the parentheses and put them in. All right, now that we've got that there, remember this thing right here? We did kind of go through this. Let's get my orange paper back. Remember this idea? Okay, what did we get there for that? You're going to remember this. You're going to remember x plus h squared. It's going to be something after you take quantitative analysis or calculus, this kind of stays in your head a little bit. So anyway, I know that's what that is. So let's put that in right there. That's going to be minus x squared plus 2xh plus h squared, right? And then also over here, I can use my distributive property. It would be 100x plus 100h. And now one more time, I'm going to go ahead and do negative. This is a negative here. This is a negative. So maybe I'll make sure I put a 1 in there. It's -1. So I'll do -1 times each of these things. It'll be negative x squared, negative 2xh, negative h squared. All right. So at this point, I have the quantity f of x plus h. I also am going to need minus f of x. That would be this, but with a minus in it. All right. So I have two important expressions that I came up with here. I found f of x plus h, which is this. And I found negative f of x, which is this. So now, remember that the formula for the derivative is f of x, f prime of x, sorry, is the limit as x approaches, as h approaches 0, of f of x plus h minus f of x all over h. By the way, that is h. Sorry about that. All right. Such a limit as h approaches 0 of f of x plus h, which I have just found to be all of that stuff. I'm going to copy it. 100x plus 100h minus x squared minus 2xh minus h squared. Good. Now, minus f of x is this quantity, minus 100 plus x squared, because that's what's here. Minus 100 plus x squared. All over h. So it's all of those terms. It's a lot of terms. Don't be afraid to write it in 2 lines. You could write it in 2 lines. You won't see that on WebAssign. They make it all one long line across. So let's see what we can knock out here. Looks like we can get rid of, let's see here. We could get rid of x squared right here. like that. All right. Oh, I think I did make a mistake. Yes, I did. Yes, I did. It's right here. Oops. Hold on, guys. Here it is. Yes. F of x is 100x. Look, 100x. There should be an x there. I knew there was something missing. All right, come back. The x was really just supposed to be right here. That was the mistake. Okay. Sorry about that. As you can see, it's tricky. Just, watch out. So now this does knock out with that. All right. You know why I knew that? Let's talk about what just happened. What just happened was I looked in the future and I thought to myself, wait a minute, this term doesn't go away. Only terms with h should be left. See, this term has h, this term has h, only terms with h should be left. What that means is when I saw 100 and 100x, they didn't really, they didn't have h in them. So looking back, that's supposed to be with negative 100x, and they do cross out. All right, anyway, now that those are crossed out, what we could do now is rewrite the formula. It's the limit for h approaches 0. And then we have what's remaining in the numerator, 100h minus 2xh minus h squared all over h. You could factor that. If you factor it, it'll be h times 100 minus 2x minus h. I didn't give myself enough room there. But looks like this. H times 100 minus 2x minus h all over h. And then they cancel. And now you have the limit of a quantity that's no longer a fraction. So from there, it's now the limit as h approaches 0 of the quantity 100 minus 2x minus h. Now, what that means is to find the limit as h approaches 0, now you're in a position where you can take that 0 and put it right there and find out what it is. When we first started, you couldn't do that because h was in the denominator and we had the issue of divide by 0. So now instead, we're going to use this expression, and it's going to be 100 minus 2x minus 0, which is 100 minus 2x. What does that mean? That means the derivative of the function 100x, if the function is 100x minus x squared, then the derivative is this. Now, I want you to get analytical with me and look at these two things. Don't they look like they have some things in common? Like they both have 100 in them. Notice this is 2x and this is x squared. They both have a 2 in them. There are connections. There are connections from when you first look at the function to what the derivative is. There are connections. In fact, they're very basic scientific connections, and that's the shortcut here. There are all these great little easy shortcuts that make this impossible long process unnecessary. All of this work I did, I could have looked at this and told you, looking at this, if the function is this, I can tell you, my friends, the derivative is 100 minus 2x. I could see it right now. And those of you who have taken calculus know how to do it too. The next part of our lesson is to figure out how to look at them and to come up with quick and easy answers to them. But when it starts, you have to understand it's about the idea of a limit of x approaching 0, and rather h approaching 0, and how it works out algebraically. All right. But I want you to remember how we worked so hard on this function using this horrible formula. This formula right here, right? We use this formula, which is really a headache. We used it, it took a long time, and we got our answer, and here it is. It's going to be really fun to show you how quick and easy it is to figure it out without the formula. All right, let's take a look at that. So what are we supposed to do? Well, our answer, like we said, is 100 minus 2x. Then part B of this question says, now find the marginal revenue when 200 when 20,000 barrels were sold. All you got to do now is just take the number 20 and put it right into that function that you just found. So in other words, take 100 minus 2x, replace x with 20, and figure out the answer. You're going to get 40. I'm sorry, you're going to get 60. And then remember, it's in thousands, so it's $60,000 is the solution. Velocity and revenue. Surprise, they're both the same exact process. Find the derivative, they're the same thing. All right. So here we go again with the slope of the tangent. Find the slope of this function at a specific point. How are we going to do that? Well, this is going to be our game plan. First, we're going to look at f of x equals x squared and work through all of this magic to figure out what the derivative is. Then we're going to plug the x value of 2 into there and get an answer. Notice that we don't particularly need to know that 4 is the y value of that point. In fact, you never need to know what the y value is when you're finding an instantaneous rate of change or when you're finding the slope at a point or anything where you substitute a number directly into your derivative at the end. You don't need to know the y value, but sometimes they provide it. It's just a matter of you recognizing that it's really about where the x value is that tells you what kind of slope it is that's tangent. So let's write down this formula. We're going to try to figure out how to get the slope of the function at 2, 4. The function is f of x equals x squared. I'm trying to figure out what is the slope of the tangent line at the point 2, 4, particularly at this x value. All right. So first, I'm going to figure out f of x plus h. Like, just dive right in. You know what you got to do. And that's going to be x plus h quantity squared. And surprise, that's one of my favorite things. I kind of know already off the top of my head. I'm thinking I'm starting to remember it. Yep, there it is again, right? Okay. So it's going to be x squared plus 2xh plus h squared. Okay, very good. Then how about what is negative f of x? Well, negative f of x would be just negative x squared, of course, right? Yeah. So if we try to figure out now the derivative here, it's the limit as h approaches 0 of f of x plus h minus f of x all over h. And that's going to be this expression, which I have right here, minus f of x, which is just minus x squared. So that you can see that, minus x squared, right? All over h. Now look, I have x squared and I have minus x squared. Don't they cancel out? They cancel out. And now I'm left with 2xh plus 8 plus h squared all over h. And then if I factor it, I can pull h out. And then if I let the limit go to 0, it becomes 2x plus 0, which is 2x. Good to know. So what is the derivative? Well, if f of x is 2x, the derivative, which is f prime of x, is 2x. But some of you might be able to see x squared and say, oh yeah, I know it would be 2x. I could figure that out right off the bat. Now, the question was saying, yeah, but what about at this particular place? What if x is 2? Okay, well, if x is 2, can you tell me what it would be? F of 2 is going to be 2 times 2, which is 4. Your solution is 4 there. Okay, so as you can see, we have another question about a tangent line. It says, given here's a function. Now please find the derivative of the function, which is an exercise that you would go through with the formula. Then find the slope of the tangent line at a particular curve, which is going to be, again, just identical to number 5. And last, it asks for the equation line that is tangent to that function. I'm going to give a little break, and I'm going to ask you to please try to figure that out for me. I give you 15 minutes. I want you to get a piece of paper and a pencil. I want you to see if you can figure it out. Use the different ideas that I just showed you. I'll put the formula back up. Actually, the formula is right there. It's right here. M equals. You could see it's right there for you. Use that function and see if you can figure out the answer. I'll tell you right now what the answer is. The derivative is going to come out to be 6x plus 2, okay? And the answer, if you plug in 1, is supposed to be 8. And then if you use 8 as your slope, and you use that 0.116, you can write the equation of the line, you should wind up with this. When we come back in 15 minutes, I'll show you all the work behind how to do that. And at that point, we'll carry on with the next part of our lesson, okay? 15-minute break, we'll come back at 5:50. And at that point, we'll talk about the results of example 6. I'm going to ask you, please try to do example 6 right now. Welcome back, students. Let's take a look at that answer. I know you guys are working on it, so I'm going to cut right to it right now. Okay, this is the work associated with example number 6 out of your text. And I just want to go through it briefly with you because, like I said, I asked you to work through it. And I know that you guys tried to do it already. So just look at the way that it's done. I want to point out a couple of important things. First, I figured out, according to what f of x is here, I went in and I figured out what f of x plus h should be by replacing every x with actually x plus h here and here, which this brought me back to my orange paper, which I remembered this is what it was. And then this was a distributive property. And then once again, we distribute here. And this whole thing here is our quantity f of x plus h. Also, by the way, if this is f of x, then negative f of x is going to be this. So to figure out f of x plus h minus f of x, I would just basically do all of this and then all of this. So here it is, all in a perfect row. Okay, and then I try to cancel things out. As you can see, there's several terms to cancel out. Something I did not mention that I meant to talk to you guys about. See how f of x plus h is a whopping 6 terms. Look at all those terms. None of them are like. You cannot combine any of them, and that's something else that makes calculus kind of ugly, is there's so much math on the paper. But you can't combine any of these little terms. None of them are like. They have to be exactly perfect to be able to combine. And that doesn't happen usually when you're doing f of x plus h. Usually it doesn't have any like terms in the result. Now, if after we cancel everything out here, we're left with a couple of terms that have h in them. There's only 3 of them. There's this one, and this one. So I've listed them here. And then I can factor out h, which looks kind of like this, factor out h. And now I have just this expression. So I'm finding the limit as h approaches 0 of that expression. And that means plug a 0 into the place where h is, which I can do now because before I couldn't do that. It was in a denominator. Now I can do that. So I put the 0 in there and it becomes the basic idea of 6x plus 2. Now, remember, we asked you a little bit more than that. We said, now, if it's, first, please find the equation of the, the formula of the slope of the tangent line. There it is. Now, what would the tangent line have a slope of if it was at a certain specific point? Take a look at the questions. It's saying the slope of the tangent line at the curve 1.16 at 1 comma 16. All right, so 1 comma 16. I'm going to use the x value here because this formula calls for the x value. What is f prime of 1? It would be 6 times 1 plus 2, giving you an 8. And last but not least, we're saying now write the equation of the line tangent at this point. So we have the point and we have the slope. Remember, the slope is the derivative. This right here is the slope. This is x1 and this is y1. So now you're in a position to go in and use any old tactic you had from back in the 9th grade to try to figure out how to write the equation of a line that goes through a point with a given slope. Use the point slope formula. All right. Y1 is 16, M is 8, X1 is 1. Distribute, and then add 16. There you go. All right. So what you've seen now is ways that you can use the derivative to answer all kinds of questions, all kinds of important questions. Questions like what's the equation of the tangent line at a given point? Questions like what's the maximum, the marginal revenue? That's really a big question. What is the velocity at a given particular point? All of these things are really big questions, and it's the derivative that gives us the answer to. But as you can see, finding a derivative is really a lot of work. So we have these wonderful little tricks that we use instead. So this is the definition of the derivative. As you can see that we've used that formula 4 times today. I think you're getting sick of it, right? But there it is. Now, this is the derivative. And if it exists, then you can use certain easy formulas like the power of x rule. Take a look at the way this works. If you go through the hard work of using f of x equals x squared, which we did, we went through that, okay? If you go through all that work, let me write on this, the answer will be 2x. If you go through the work of doing it to x cubed, which is, you can imagine, that's x plus h, x plus h, x plus h. I mean, it's a lot of work, right? But if you go through all that work, you're going to get this as your answer, 3x squared. If you do x to the 4th, you'll get 4x cubed. If you do x to the 5th, you'll get 5x to the 4th. Look closely there. Do you see a pattern? It's as if I took the exponent, dragged it down to the front like it was the coefficient, and dropped the exponent by 1. For example, x3 gives you 3x2, right? Think about that. x5, 5x4. See that? There is a pattern there. So if I asked you what is the derivative of x to the 5,000th, it's really not hard to figure out if you use this little pattern. But if you use the function, the limit formula you see there, I mean, it's really horrible. So that's what we're learning about now, is all the tricks of the trade of finding derivatives. That way you don't have to go through all of that old hard method of finding the limit the way that you see there. And it's important in chapter 9.3 to work through all of that math and to be comfortable with all of that reasoning so that you can assume that the power rule works and the other rules associated with derivatives work. I want you to think of it this way. These rules are in place because that limit function formula yields these kinds of answers. And since we can see that pattern, we use that pattern to get quicker answers to derivatives than going through that whole big nasty fraction. That's what the idea is. So let's take a look at some of these. Powers of x rule. If we have something like x to the n, it's like n times x to the n minus 1, right here. The exponent becomes the multiplier in front. Powers of x rule. So we just talked about that. And now we're going to do it to a couple of examples here. And I want to show you just what I'm talking about and how to get them. So I don't think I have to write them. You should be able to see them by the answers. The first one, can you imagine, it would be 14x to the 13th. How did I get that? I took the exponent 14, brought it to the front, and dropped 14 by 1. So it's 13. Now, let's do it with a negative number. The coefficient should be -2, but let's take -2 and subtract 1. What do we get? What's -2 minus 1? Don't fall into that trap. You know what it is. It's -3, isn't it? Yep, that's what the answer is this time. So the derivative of x to the -2 is, just like you think, the exponent becomes the coefficient, -2x. Now lower the exponent by 1. So -2 minus 1 is -3. How about y equals x? Well, don't forget x is actually x to the 1, right? So for some reason, it turns out to be 1. Isn't that strange? Why does that work? Well, let's take a closer look at that one. X to the 1. Okay, so let's bring the 1 down. And if I'm writing the derivative, I don't write y equals, I write y prime equals, because that's not y, it's y prime now. Bring the 1 down to the front, write the variable, and now what is 1 minus 1? It's 0. Okay, trivia question. What is x to the 0 power? Anything to the 0 power forever and ever, amen, is always 1. So this has become 1 times 1, which is 1. So what is the derivative of x? The answer is 1. There you go. Likewise, what is the slope of the line y equals x? The answer is 1. Surprise. And while we're on the paper, let's talk about x to the 1/3. Yep, x to the 1/3. How do I find the derivative of that? Well, it's going to be, of course, if that's y prime will be 1/3 x. And now I got to figure out what goes in this box here. We'll put there with the exponent. To think of 1/3 minus 1. Well, you could do it with a calculator. You could do it with the old school method, but you're going to get negative 2/3 anyway you look at it. And I want you to look at how ugly that is, man. That is nasty. You got a fraction as a coefficient, a negative fraction as an exponent. It's nasty, but let me tell you, you just have to carefully do your arithmetic correctly, and voila, you will get the right answer. There it is, the very dreaded negative 2/3 exponent. There you go. All right. Now, in the same regard, we can do this with more advanced ideas, and as you can see, what we have here is just applications of old ideas that we're supposed to already know. For example, we could start by using different variables. So u of s equals s to the 8th, and that's really cute. Let me write that a different way. Hold on a minute. S to the 8th. S is the worst of all. I'm telling you, when it comes to writing equations and doing math, the letter S looks so much like the number 5. It really is very confusing. So they're putting that in there to try to get you, but you should know better. U prime of S then is going to simply be 8s to the 7th. Not hard. Okay, that was one of them. The next one is we have strange letters, and the letters are P equals Q to the 2/3. Again, employing all of the ugliest letters of the alphabet. We're going to figure out the derivative by saying it's P prime. And it's going to be that exponent, 2/3, Q. And now I have to think about 2/3 minus 1. Okay, back in 4th grade, we learned this. The answer is negative 1/3. Nasty, but that's what we were looking for, negative 1/3. The next important one we're going to do is C of t equals the root of t. So, trying to figure that out now. T under a root is also known as t to the 1/2. So C of t is really t to the 1/2. Why? Well, because the index here in the square root is actually 2. It's a square root after all. And if I put a 3 there, you'd know it was a cube root. If I put a 5 there, you'd know it was a 5 root. But it's a square root, which means it's a 2. Can we remember that when you have a root, the index, which is the number in there, is the denominator of the exponent? That's something that we learned a while ago, but I need you to remember that because that's going to come up over and over again. When you see square root of t, it's exactly the same as t to the 1/2. All right? Now, let's figure out c prime of t, meaning let's take the, let's take the derivative of that function. Well, it's going to be that very exponent I see there, 1/2. And now I have to think about what is 1/2 minus 1? And the answer is negative 1/2. See, don't get lost in these little silly fraction questions. People see those fractions and they freak out and they go, oh, I can't do this, is so hard. You know, fractions are really not that bad, especially in calculus. They're not really that horrible. I mean, 2/3 is, a little ugly, but it's not as bad as it could be. It could be a lot worse. The last question that they ask is s equals 1 over the square root of t. So, in the same way that we talked about the root of t is 1/2, well, 1 over the root of t is negative 1/2. So I'm going to actually act as if this is written this way, s equals t to the negative 1/2. And now I have to be very careful. If I'm finding the derivative, I first write that exponent just the way I see it, right? Negative 1/2. And be clear, make it very clearly negative 1/2. And then t. And now I have to think about negative 1/2, negative 1. What is that? Negative 1/2, negative 1 is pretty crazy, You use a calculator, figure it out. The bottom line is it's negative 3/2. Okay, and that's what we were trying to go for that question. So for this one, it was just 8 to the 8s to the 7. Here we have 2/3 q to the negative 1/3. We have a half t to the negative 1/2, and we have negative 1/2 t to the negative 3/2. Now, I know that later on you guys are going to come back and watch this video and think about this, and I'm hoping that you remember me saying one thing. It follows the exact rule it's supposed to. If it's a fraction, subtract 1 from the fraction. If it's a negative integer, subtract from a negative integer. In other words, do just what it tells you to do. Do exactly what you're supposed to do there. Here's your answers. And the dreaded -3/2, there it is, right? So I hope that helps a little bit. And as you can see now, we have some really basic ways to, I would definitely rather do this stuff here than that horrible limit formula with the fraction and all that stuff. You know what I'm saying? So it's much easier than the other method. All right. Now, we do have that power rule, and we can use that a lot. Let's take a look at how we could use that to answer a question from before to make it much, much easier. All right. The question is, write the equation of the tangent line to the graph at y equals x cubed at x equals 1. We want the equation of the tangent line at x equals 1. This is an age-old calculus question that you hear over and over and over again. Write the equation of the line that is tangent to this function at this point. It's basically what it means is take the derivative, plug that in to get the slope, then use that as the slope and write the equation of the line. By the way, if x equals 1, y is going to be 1 cubed, which means it's also going to be 1, which means that this is the point 1 comma 1, and that will come into play later on when we're trying to write the equation of the line. That's going to be our x1 and our y1 in our formula for the point slope. First, let's figure out what is the derivative. Now, the good news is I don't have to find the limit. I can use my trick. My trick is the derivative is obviously 3x squared, is it not? Right, that is our power rule. We already know that. Now, what is the derivative at x equals 1? Y prime of 1 is going to be 3 times 1 squared, which is 3 times 1, which is 3. Meaning the slope of that tangent line is 3. And now you're back in the 9th grade, writing an equation of a line that has a slope of 3 at the point 1, 1. So I hope this is making sense. It's applications of different things you've already learned, but here's your solution written out. And I want to focus with you a little bit on the actual idea of what's really going on. Guys, please focus with me right here. Right now at this point, I'm looking at this part of our presentation right here. Right? The blue line there is the tangent line. The point is a point that was selected on the graph to prove some kind of reasoning. At the specific point 1, 1, the tangent line has a slope of 3 and has an equation of 3x minus 2. We can use that for all different reasons. You can use that to answer all different kinds of questions in finance, in medicine, in economics, in all kinds of great contexts. The point of it is, when you're asked to find the equation of a tangent line, you need a slope and you need a point to write an equation of a line. You can get the slope if you know the function, its derivative, and the x value of the point. That'll tell you the slope of that line. That's the process that we're going through here. All right, now, in the same way that we had the powers of x rule, we have a whole bunch of other little rules that are really actually very basic and that we don't have to worry too much about, but they follow and they kind of make sense as you do your practice. First of all, we know our power rule, it's right there, it makes sense. Then we have the constant rule. The constant rule is really very simple. If it's f of x equals a number and there's no x in it at all, the answer is 0. For example, instead of f of x equals x cubed plus 5x, say I give you f of x equals 30, just a number. The derivative is 0. The derivative of any number is 0. Then the derivative of any term is going to have the derivative of any constant that's being multiplied by a whole function you could just do the derivative of the function and multiply later on. In other words, you could take the derivative out. I'll show you what that means in writing in a minute. The sum rule and difference rule are basically the same rule. In other words, if you have many different things added and subtracted, like in a polynomial, you could just go along and take the derivative of each thing in the list. That's what they mean, the sum rule and the difference rule. Let's look at some examples, it'll become clear. So what's the derivative of y equals 4? Very simple. The answer is 0. Why? Because the function this time is a constant. All right, let's look at this one. Here's some derivatives. Here's some constants we can talk about. First, see how this one is 4x to the 5th? The idea is that you can actually act like the 4 is not there for a minute, and then go and do x to the 5th and come back and multiply later. I'll show you just what I'm talking about. In the case of find the derivative of 4x to the, what was it, 4x to the 5th. In the case of figure out 4x to the 5th, to find the derivative of that, what you would do is you would think about how, well, there's a 4, that's a constant. So I'll write the 4, and then I'll figure out the derivative of x to the 5th. So let's stop what we're doing and figure out the derivative of x to the 5th. Is it not 5x to the 4th? It is, right? Okay, so now let's simplify. And what is 4 times 5x to the 4th? The answer is 20x to the 4th. Now, this is what we call the constant rule. Now, people don't usually think of it this way. People instead just think I take this number, and if there is a number here, I multiply it by that number. In other words, 20x and then lower it by 1 like that. And either way you think about it, it is going to wind up being the same both ways. But the reason why you can take the liberty of doing the exponent multiplied by a constant if there is one is because of this concept of the constant rule there. All right, let's take a look at the next one. It's saying, how about 1/2 t squared? If it's 1/2 t squared you're trying to find the derivative of, ignore the 1/2 for a minute and then just find the derivative of t squared for a minute. What is the derivative of t squared? It is going to be, after all, 2t to the 1, right? Now, what is 1/2 times 2? It's 1. What is 1t to the 1? It's t. So these little ideas all follow basic concepts that you already know from arithmetic and algebra. It's just a matter of now applying them to try to yield correct answers for questions like this. So there's the, that one is t. And then when it comes to part C, what we're going to do for part C is we're going to use, again, for Q, -1/2. And if you use -1/2 with that 5 there, it turns out looking like this. Let me show you what that would turn out to be. It's P equals 5 over root Q. All right, 5 over root Q, we're going to rewrite that to be 5 times Q to the -1/2. Now, if we're taking the derivative of that, I can first take the derivative of Q to the -1/2. And when you do that with the line, that means you're taking the derivative of it. And this is something we actually already did somewhere along the way. If you recall, we got this for it. We got -1/2 Q to -3/2. Remember, we talked about how ugly that looked. But now, we can now apply the 5. In other words, we ignored the 5 for a minute and focused on just getting the derivative of this part. And when we're done, we're going to multiply our answer by the 5 later on. Now, 5 is over 1, by the way, remember that? So it's going to be -5 twos Q to the -3/2. Like, I hate that word halves. I try to say twos, which is inappropriate, but I don't care. All right, so there you go with that question. I hope that was clear. Let's talk about an application now. We're talking about world tourism. World tourism has grown into one of the world's major industries. Since 1990, the receipts from world tourism, Y, in billions of dollars, can be modeled by this function. Okay, remember, it's whatever you write down, y equals 16 is 16 billion, right? You can even get away with writing the word billion, B-I-L-L-I-O-N sometimes, all right? So we have a little function. It's a pretty basic function. It's not that hard. X is the number of years past 1980. Okay, we have a line in the data. For example, if it's 7, it's 1987, etc., etc. First, name the function that models the rate of change of the receipts from world tourism. In other words, find the derivative of this function. Modeling the rate of change is the same as finding the derivative of. They mean, again, the same thing. So how would you do that? Well, you'd think first about 1.18 times 15.9. And what would you get? Let's take a look here. You would get, oh, name the function. The name of the function is the derivative. Okay, great. B, find the function. Okay, here we go. We'd multiply 1.18 times 15.9 to get that strange number, 18.762. Now take 1.18 minus 1, and don't you get 0.18? Okay, so now what you're doing is you're using crazy decimals in there, but you're still following, like I said, the same mathematical principles that we all know already, like how to subtract 1 and how decimals work and things like that. Okay, last, find the rate of change in world tourism for the year 2020. How would I do that? Well, the year 2020, in this case, is the number 40 because it's the number of years since 1980. So in other words, now take that derivative you just found and put 40 in there. And when you put 40 in there, you're going to need a calculator for that because of that funny exponent. You get that as your answer. All right. That's the idea of how to use those little shortcuts about the power rule, the constant rule, and so on to try to answer questions in a real world situation like that. Now, for the next couple, we're going to talk about the algebra of the sum and difference rules. For the most part, I want you to look at each of these as if they're a bunch of little questions all at once. For example, I'm going to draw on the page to show you. You already know how to figure out the derivative of 3x. Because of the constant rule, the answer is 3. Right? You already know how to figure out the derivative of 5 because of the constant rule, the answer is 0. So the answer here is 3 plus 0, which ultimately is 0, right? And 3 plus 0, which ultimately is 3. What am I saying? So there's your answer, 3. The same thing goes with the next one. For the next one, just find the derivative of 1/3 q to the third. Then find the derivative of 2q squared. Then think of the derivative of -3, which is nothing. And then you'll get that for part C. That's C right here. Make sure you use the correct letters. That's another thing that's important. And basically, these are all sum and difference rules. Means just do each little one and write each answer to each one. If you have a constant, remember the derivative of a constant is 0. So there's just nothing to be written for that. Just do one at a time and write the answers for each one, and you'll get the thing right. All right, and that's what they do with the sum and difference rules. I invite you to go through those questions and think about how that works. And last but not least, for example, 8, suppose that t is the number of years past 1960. And now you have a function here. It says this is going to model the U.S. total personal income in billions of current dollars. For 2018, find the model's prediction for the U.S. total personal income and the rate of change of the U.S. total personal income. So for this one, what we're going to do, once again, surprise, you're going to find the derivative. And after you find the derivative, then you're going to plug in a specific number for 2018. 2018 is going to be 58 years past 1960. So these are the answers you're supposed to get for something like that. The first question is asking you to find the model's prediction for the U.S. total personal income. That's actually, you can't find that unless you could first find the derivative. So as you can see there, where the derivative is written, and then after you find the derivative, which is part B, then you will go back and plug in your 58 and get your solution. You're using 58 because 2018 is 58 years beyond 1960. Now, I don't want to work through each of these with you with the marker because you've seen a lot of great cases today of me finding derivatives for you and using derivatives and applying it with algebra. You don't need to see me drone on and on about it. I have a feeling very many of you are probably kind of beaten, tired from all the math I've been barking at you, but I did want to try to make everything as clear as I could, and I hope it was inspiring because I know it can really drag. It could be a little bit tricky, but anyway, let's carry on now here. Okay, we have a couple more little examples, and then we're almost done here. This one is about revenue. Couldn't let it go without doing revenue. So it says, suppose the manufacturer of a product knows that because of the demand of the product, the revenue is given by this particular formula. X is the number of units sold. Find the marginal revenue at X equals 500. Well, if I need to find the marginal revenue at X equals 500, then first I better find the marginal revenue. The way I do that is simply by taking the derivative. So What I would do is I would take 1500x minus 0.02x squared, and that's r. And then I would find r prime, which is this right here is the constant, not the constant, but this is the basic power rule or coefficient rule, 1500. And then I would take 2 times minus 0.02, which is minus 0.04, and then lower that by 1. And then I would take this answer and figure out what is it for 500, and figure out 1500 minus 0.04 times 500 to get my solution. So figuring this out, you would get that figure 1480. And then last, it says, find the change in revenue caused by the increase of sales from 500 to 501. The way you're supposed to figure that one out is by simply looking at the derivative. So let me change this. There we go. We'd find r of 501 and find r of 500, and then subtract them. Okay, so that's how you would go about doing that question. And I hope that that helps you guys. I hope that it's really clear for you. Let's take a look. That's all I have for you. I knew that was about the end. It is 6:21. Our class officially dismisses at 6:45. So what I'm going to do is I'm going to stop our share and I'm going to stop our recording. I'll open up the floor to any questions that you might have. If there's anything that you'd like to talk about, and then we'll dismiss for the day. So thanks again, my friends, for paying close attention to my lesson. And please let me know if you have questions with the website.